Hello, everyone. My name is Kevin Ayala, and I am an undergraduate physics researcher at the UNLV. Now, one of the most fascinating things about physics research is that we can actually study materials at the subatomic level. For example, in the field of condensed matter physics, which is actually one of the areas UNLV specializes in, we can study materials, like I said, in the subatomic level, but at extreme conditions. That is, how do materials behave at high temperatures, high pressures, or even irradiation? Now, to be more specific here, the research I am doing is under the guidance of Dr. Michael Pravica. And what he has done is that he's been utilizing X-rays to blast materials, and from this process, complex chemistry has occurred such that we've been able to synthesize fascinating materials. Now, more specifically though, I am very interested in a material he synthesized called polymeric CO, or poly-CO for short. And the reason for that is because it stored CO2 for a very long period of time. And this implies this material could be used for solid fuel rocket propellant. It also had electrical properties like those in wide bandgap semiconductors, which are used in our LED lights and our solar cells and so many other things that we use in our everyday lives. Also, it had optical second harmonic generator properties, and therefore this material can be used to create powerful lasers. So, the question then becomes, can I produce this material in a more efficient way without X-rays? And that is the purpose of my research. And for this one specifically, I've been utilizing high pressure environments to see if anything occurs with material. And the mechanism we use that for specifically is called a diamond anvil cell. And it is a very simple mechanism. All it is that there's a small cell containing a diamond in it. And then we place a small amount of material on a Q-lit face. We also put a ruby in there so that we can measure pressure later on. We get another cell with another diamond in it. We close it up. And then just applying small amount of forces in the diamond anvil cells can generate large amounts of pressure. Gigapascals, which is 10,000 larger than what we feel right now. Also, to analyze the material, you might be questioning, we use a technique called Raman spectroscopy, where we shine a special type of light through the diamond anvil cell, and from here we obtain graphs that I have here, where each peak corresponds with different bonds of the material. So to get into my studies here, first I did barium oxalate, and I went up to 51 GPa. And only two important things came out of it. First, I noticed that this peak here split into two, and that could indicate a phase transition, or in other words, the crystal structure of the material just changed. Now, as a qualitative behavior, the material did become translucent around 15 GPa, that is, light started shining through it. And those are the two major findings I found for that study. Now, for the tin oxalate, I went up to 31 GPa, and what happened is that as I increased pressure, the second and third peak started shifting to the right and left respectively. And this could imply a weakening of a bond or even an electron transfer, which I will talk more about in a bit. Lastly, there was this qualitative, interesting behavior of the material, where it changed from a white to an orange to a red to a really dark red. And as we decreased pressure, it stayed in this kind of golden yellow color. And of course, this could be explained by this electron transfer I'm talking about. Now, going into my last study with lead oxalate, the Raman spectrums were a bit different compared to the tin, but it did also change color as how tin did, but at a much higher pressure since we went up to 64 GPa here. And this could be mainly due the differences in the Raman spectra could be due to the differences in the electronic configuration, or in other words, the molecular orbitals of this system here. Now, let me go more in depth about this electron transfer I'm talking about. So specifically with the tin, we believe as we increase pressure, we're actually overlapping molecular orbitals of the tin oxalate anion and the tin cation, such that there's an exchange interaction among the electrons, where the electron actually becomes confused and is actually transferred to a different region in space. Now, why is this even interesting? Well, we are actually seeing chemistry in a very slow motion where normal chemistry actually occurs in femtoseconds, we are controlling it at a very slow manner. We are perturbing these intermolecular interactions, which is quite a fascinating sight, and therefore allowing us to do that will allow us to actually control these routes of chemistry and therefore make new materials. Now, as conclusion of this whole project, I did 3 pressure studies: barium, tin, and lead oxalate. But I will need further investigations such as X-ray diffraction to further study these materials, and also what happens with temperature, and also different irradiation studies. So I still need a lot more to do to fully understand these processes, but of course, this field shows promise in creating new radiation-hardened materials that could benefit us in many diverse ways. And of course, this is just our first step. Thank you, everyone, for coming to my presentation. I hope you guys enjoyed it. If you guys have any questions, my information is down below, and I hope everyone stays healthy. Thank you.